Assalamu alaikum. Today is lecture 11B, second part of lecture 11. And in last lecture 11A, we discussed about the result in which the first part of the result is if A is congruent to B modulo P, then the Legendre symbol of A over P is same as Legendre symbol of B over P. Where A and B are integers, P is an odd prime and P does not divide the product AB. The second part of the theorem is the Legendre symbol of A over P times Legendre symbol of B over P is same as the product Legendre symbol of the product A and B. And the third part states that the A square of any Legendre symbol of the square of any integer over A prime is always equal to 1. We have proved all the parts in the last lecture. So on the basis of these three statements, we can infer many things. For example, the first thing is if A is congruent to B modulo M, then this must be P. Modulo P, then either both are quadratic residue or both are quadratic non-residue. Because both are quadratic residues or both are quadratic non-residue. The second thing is the product of two quadratic residues or the product of two quadratic non-residues is always a quadratic residue. It is same as that the product of two positive is again a positive, or two positive or two negative is again a positive number. So always a quadratic residue. So if two numbers are quadratic residues, then their Legendre symbol is 1. So product of 2, 1 is always 1. And if two numbers are quadratic non-residues, then their Legendre symbol is -1, then the product is again 1. Okay, so in both the cases, in both of the cases, the quadratic residue, so we have a quadratic residue. Okay, but if or the product the product of one quadratic residue and one quadratic non-residue is always a quadratic non-residue. For example, minus 1 times 1 or 1 times minus 1. So if the two numbers are quadratic, if one of them is quadratic non-residue, then one of the Legendre symbol of one of them must be minus 1, then product will be minus 1. Okay. The square of, and according to the third, the square of any integer is always a quadratic residue. Okay. So for example, if we have like a square times b, and we need to find the quadratic residue, so we can combine two and 3. So by 2 we can write a square, Legendre symbol of a square, times Legendre symbol of b, and according to third, Legendre symbol of a square is 1. So 1 times b. So if we have a square of any integer which is and p is not dividing that integer, so in that case uh, in that case the Legendre symbol will be equal to b. Okay. Okay, let's have a result, corollary of this result that we discussed earlier. It's corollary. Okay, let me number it 2. If p is an odd prime, then Legendre symbol of minus 1 over p is equal to minus 1 to the power p minus 1 by 2, that is minus Legendre symbol of minus 1 is equal to 1 if p equals or p congruent to 1 modulo 4, and minus 1 if p congruent to minus 1 modulo 4. Okay, move to the proof of this result. By Euler's criterion, we can apply Euler's criterion here. By Euler's criterion, Legendre symbol of -1 over p is congruent to -1 to the power p minus 1 by 2 modulo p. Okay, so this value is equal to -1 to the power p minus 1 by 2, because we know that -1 to the power p minus 1 by 2 is either plus 1 or -1. Okay, so this thing can also be written as 1 if p is of the form 4k plus 1, because if we have p of the form 4k plus 1, so -1 to the power 4 -1 to the power 4k plus 1 minus 1 divided by 2 is equal to -1 to the power minus plus 1 minus 1 cancel, 2 under 2, 2 times 2 is 4. So -1 to the power 2k, where k is an integer. So this is always plus 1. So if p is of the form 4k plus 1, then this is always 1, and -1 if p is of the form 4k minus 1 or plus 3. Okay, for example, -1 to the power, if p is of the form 4k plus 3, then -1 divided by 2. So this is -1 to the power 3 minus 1, 2. We take 2 as common from here. So this is 2k plus 1 divided by 2. 2 cancelled, and this is -1 to the power 2k times -1 to the power 1. -1 to the power 2k is 1 times -1. So this is -1 always. Okay. So 1 if p is of the form 4k plus 1. So when this, because p is in the form 4k plus 1, so whenever we divide this by p, we will get remainder. Whenever this number 4k plus 1 is divided by 4, we get remainder is equal to 1. So we write if p congruent to 1 modulo 4, and -1 if p is congruent to, whenever we divide this number by 4, we get remainder equals 3, and 3 is same as, or 3 is congruent to -1 in modulo 4. So that's the required proof. Okay, look at some examples. For example, minus 4 by 83. 83 is a prime number which is not dividing 4. Okay, so this can also be written as 2 square times -1 by 83, and this can also be written as 2 square by 83 times minus 1 by 83, and this is same as this must be 1 because this is a square, so 1, and by previous theorem this will be minus 1 to the power 83 minus 1 divided by 2. So 83 minus 1 is 82. 82 divided by 2 is 41. So minus 1 to the power 41 is a negative number. So this is equal to minus 1. So Legendre symbol of minus 4 over 83 is minus 1, or you can write. Okay. Let's have another example. 32 or 41. Okay. So 32 over Legendre symbol of 32 over 41. So 41 is not dividing 41. Okay. So this 32 can be written as minus 9 by 41. Okay. And because we don't have, because 32 is 2 to the power 6, but we don't have the Legendre symbol of 2 over 41. So we write alternate minus 9 over 41. So this minus 9 can be written as 3 square times minus 1 over 41, and this can be written as 3 square, Legendre symbol of 3 square times minus 1 41, and this is equal to Legendre symbol of 3 square is 1, and Legendre symbol of minus 1 is minus 1 to the power 41 minus 1 by 2. So minus 41 minus 1, 40, 40 divided by 2, 20, minus 1 to the power 20 is plus 1. So this is 1. So 32 is a quadratic residue over 41. Okay. Otherwise, without these rules, it is very difficult to find whether 32 or minus 9 is a quadratic residue or not. Okay. Okay, let's have another corollary, which is Corollary 3. Let P be an odd prime Q a prime such that P does not divide another prime Q, and I a positive integer then Q to the power I, Legendre symbol of Q to the power I is same as Legendre symbol of Q whole power I. Okay. So by using this result, we can find the Legendre symbol of different integers. For example, if Legendre symbol of 5/17 is -1, then Legendre symbol of 125/17 can be computed by using the above rule. This can be written as 5 cube 17 or 5 Legendre symbol of 5 whole cube. So this is -1 -1 cube, and this is -1 again. Or you can find the Legendre symbol of 125/17 by using the results that we discussed previously. Means 125 can be written as 5 squared times 5 equals 5 square 17 times 5 17 equals Legendre symbol of 5 square is 1, Legendre symbol of 5 is -1, so this is -1 again. Okay, we have another corollary, and we call it corollary 4. Let P be an odd prime and let pi to the power pi limit from 1 to n means the product of primes pi to the power ei be the canonical decomposition of A where Legendre symbol of P equals 1, then one to n pi p to the power ei. Okay, let's apply this corollary in different cases. For example, the Legendre symbol of this is an example. Legendre symbol of 2/23 is 1. It is given here. And Legendre symbol of 5/23 is also is -1. So we can compute Legendre symbol of 5000/23. So we can find the canonical decomposition of 5000, which is 2 to the power 3 times 5 to the power 4. Okay, by 23. So now we can use this result. So according to this, 2 Legendre symbol of 2/23 to the power 3 times Legendre symbol of 5 to the power 4, and this is given here 1 to the power 3 and -1 to the power 4, so this is 1. Okay, so thank you. We will discuss Gauss lemma in the next class, inshallah.